All right, good morning and welcome everyone to this special Reading Week edition of Trainee Talks. Trainee Talks is a monthly webinar series showcasing the research topics of our CREATE graduate students in their area of interest related to software engineering and AI. My name is Lori Akiyama and I'm the program coordinator for CREATE SE4AI at Concordia, and I'll be moderating the webinar today. Today, we are pleased to showcase two more of our program trainees, Altaf and Musfiqur, as they share their ongoing research with our group. Altaf Abbassi is a Master of Science student in software engineering, specializing in AI at Polytechnique, Montréal, under the supervision of Dr. Musfiqur. Her research focuses on ensuring the quality of ML-based systems in production. With academic experience across Tunisia, Germany, and Canada, and industry experience in software development and ML ops, she is passionate about advancing AI-driven software systems while actively promoting women in engineering. Altaf will be sharing her research on ReCatcher, a novel regression testing framework designed to systematically compare and assess the code generation performance of LLMs. Immediately following, we will hear from Musfiqur Rahman, a PhD student in software engineering in the DAS lab at Concordia University, under the supervision of Professor Imad Shihab. Mushi has a master's degree in computer science from Concordia and a Bachelor of Science degree in computer science and engineering from East West University in Bangladesh. His research interests include mining software repositories, machine learning, and C4AI. Today, Mushi will be sharing his research on the impact of environment configurations on the stability of AI-enabled systems. This webinar is being recorded and will be available to view on our CREATE website at c4ai.org and also on our YouTube channel. So I'd ask you that if you please keep yourselves on mute until the end of each speaker, and then we'll open things up to question and answer from the audience. So we're 33 people today, really happy for the great turnout. And with that, I will turn things over to Altaf, who is going to appear as AA to everyone. So go ahead.
Hello, everyone. So can you see my screen, please?
Yes, we can.
Okay, so hi everyone. So I'm Altaf and I'm AA from the video. My name is Altaf. I'm a master's student at Polytechnique Montréal. I work under the supervision of Professor Musfiqur. And today I'm really happy to share with you our ongoing latest research titled ReCatcher towards regression testing for LLMs in code generation. So for this presentation, we will start by giving an overview of the problem, then detail our approach, present our results, and we will have a conclusion at the end. So LLMs, generated code, are kind of designed to be integrated into production code base, and they are going to be more powerful and more and more good. So to the point that the CEO of Alphabet, which is Google, mentioned that 25% of Google code is written by AI, and this is just the beginning. And this was October 2024. So now we believe it is more than the 25%. So a question here could be: are LLMs perfect in code generation? Are the generated codes perfect? Do we have logical correctness issues? Basically, unfortunately, the answer is no. Given a simple task here from human eval that states given a positive integer n, return the count of the numbers of n digit positive integer that start or end from 1. We can see here that like the specification are clearly mentioned that we need numbers of n digits. Unfortunately, when we generate the code using GPT-4o, one of the latest, more powerful GPT model and LLM, the generated code totally overlook the condition of being numbers of n digits, given a wrong formula for that. At this point, we say that given the simplicity of this task, given the requirements are already clearly mentioned in the task description. However, the LLM model, even if being a very capable model, is enabled to generate a correct code for this. But what about beyond correctness? At this stage, we know already that even more capable and very capable LLM model can fail to generate correct logic. But is that the only inefficiency that occur in LLM-generated code? Unfortunately, again, the answer is no. Here we have another task, also for human eval. The task is very simple. It basically checks if given a list, we can have two close elements in this list or not. A very simple, and the task is really well documented. However, although being a correctly logic method, the generated code by GPT-4o Mini uses nested two loops, resulting in a time complexity of O(n) squared. This code is not efficient in terms of time. This code could be easily improved and optimized by sorting the list first and having only one loop to have a time complexity of n log n and only. I need to mention here that GPT-4o Mini is like a really powerful model, and it has a top at one results even more capable than the GPT-4o model. So at this stage, we know that LLMs are not always good in generated correctness, and even when correctness is good, we do have other inefficiencies. So our goal here, or our first goal, is to study the inefficiencies in LLM-generated code. What are the inefficiencies, the overall inefficiencies in these generated codes? Then after that, our second question that came to our mind is that, like, is logical correctness enough to compare between models? Almost all the comparison between models is done with logical correctness. Given, like, for example, the human eval leaderboard or any leaderboard, they basically all of them just use the correctness rates. Let's imagine a scenario here. We have an LLM user that wants to migrate from GPT 3.4 Turbo to GPT-4o Mini, given that GPT-4o Mini is more capable and more cost-effective and smaller model, resulting in less overhead. The GPT 3.4 Turbo has a pass at 1.8 with 70%, while GPT-4o Mini, it is 83%. So GPT-4o Mini is more capable in terms of generating correct logic. Here we have the same code from the previous slides, or the same task has close element, checking if we do have neighbors or not. For example, here in the GPT-4o Mini, we use nested loops, resulting in O(n) squared time complexity. However, for the GPT 3.5, the solution is much more optimized. They start by sorting the list, then they only have one loop, resulting in O(n) log n time complexity. So here we can say that in terms of performance, 3.5 can be better, or maybe better, but in terms of logical correctness, GPT-4o Mini is better. The question is, like, how to make the decision about migration. That's why here we need, in an urgent need of regression testing for LLMs in code generation that will help to guide the LLM users to make more informed decisions about the model or the LLM they are currently using. To summarize about the study goals, we are we are interested in the quality of LLM-generated code. Our first goal is to investigate what are the inefficiencies in LLM-generated code beyond correctness. And our second goal is a regression testing framework for LLMs in code generation. So we proposed a framework called ReCatcher. Now let's start with our approach. Our first goal is we wanted to investigate what are the inefficiencies, and we are proposing taxonomy of inefficiencies in LLM-generated code. Given a bit of time limits, I'm not going into details of the methodology and the results of this first goal. However, overall, we analyzed the 492 LLM-generated code by 3 leading models, CodeLama, DeepSeek, and CodeGemma. These code snippets were analyzed, and we investigated inefficiency patterns to construct a taxonomy of inefficiencies. This taxonomy is composed of 5 main categories and 19 subcategories. This taxonomy was validated with 58 practitioners and researchers. So here we have an overview of the taxonomy. Our taxonomy is mainly 5 main categories. We have general logic, performance, readability, errors, and maintainability, with 19 different subcategories. These 5 categories and the whole taxonomy can be mainly even more categorized into 3 main aspects of code quality. The first one is correctness of the code, where we have general logic with missing the exception handling, wrong logic, partially wrong logic, and wrong method input. Then we have the static issues. We have readability, errors, and maintainability issues regarding variable naming, regarding the readability of the code. For errors, we have syntax errors, missing variable declaration, and missing module import. Finally, for maintainability, we do have inefficient conditional blocks with duplication issues for code and for comment. And finally, the last big category is performance. So we do have mainly two subcategories: inefficiency in terms of time, inefficiency in terms of memory. When it comes to time, we have inefficient iterative blocks, AVIA initialization condition or stopping condition. Then we do have suboptimal time complexity, redundant steps, and unnecessary steps. At this stage, we kind of have results, or kind of we have outputs for our first goal, which is understanding the inefficiencies in LLM-generated code. Regarding our second goal, which is proposing an LLM regression testing framework for code generation, we propose a framework called ReCatcher. Basically, given an overview of it, we have as input 2 models, LLM1 and LLM2. Then we have the framework, and as output, we have a very detailed kind of report, regression testing report. For example, here stating that we have improvement 50% in terms of correctness. However, we have decrease in with 8% in terms of performance. The goal of ReCatcher is to assist users to make informed decision about migration. For example, if the user is in situation where there is limits regarding the resources, he will probably refuse this migration. However, if the priority is logical correctness, he will probably approve this migration. As overall workflow, we start by 2 LLMs. Then we generate the codes using a benchmark. The benchmark could be like human eval, code eval, or any private code generation benchmark. Then we have the backbone component, which is the test suite. The test suite basically is what we implemented is like 3 big main dimensions: logical correctness, performance, and static quality issues. This component is highly customized and configured, so easily you can activate, deactivate, or extend this test suite. And the output of the test suite will be like concatenated, aggregated together to have the final report that will assist users to make their informed decisions. Now let's go deeper into the test suite component. To construct the test suite, basically we relied on the taxonomy we proposed. So we have issues regarding general logic, regarding performance, and regarding static code issues. We mapped each category to one or many metrics. For instance, logical correctness is mapped to the rate of incorrect logic. Performance in terms of time and memory is mapped to the rate of tasks that showed improvement and to the rate of tasks that showed regression in memory usage and execution time. Then for the quality issues, for the errors categories, we have the rate of syntax errors, the rate of missing import declaration. For the readability, the rate of confusing variable naming, subreadable code, maintainability. For inefficient conditional block, we have the rate of unnecessary else, unnecessary conditional block, and the duplication either for code and command. To have the output of all of these metrics, basically we relied on external tools. For example, for logical correctness, we executed the unit tests and we report the results. For performance, we repeat executions many times, then we do a statistical test to say if there is actual difference between the two codes or not. Finally, for the static code issues, for the duplication issues or code clone issues, we used a tool called copy paste detector, tool CPD PMD. Then for the rest, we used the Pylint, which is Elanter for Python programming languages, given its wide popularity and advantages in terms of overhead and easy to apply. Now we had kind of a big overview of the regression testing framework. At this stage, we want to use ReCatcher to assess or to evaluate regression between two models. So we have two scenarios. The first scenario is GPT 3.5 Turbo vs GPT-4o, then GPT-4o versus GPT-4o Mini. As benchmarks, we used the Human Eval Plus, like the really well-known code generation benchmark, and we used also Big Code Bench. Big Code Bench offers 1,140 tasks, and what's good about it is that more than the programming tasks, we have more various tasks regarding web development, machine learning, data analytics, and also security, given better evaluation for LLMs in a real context use. We repeated each code generation 10 times. For performance, we execute each code 5 times, and the reported values represent the average. So let's start with the first scenario. For the numbers highlighted in red showed regression. Numbers highlighted in green showed improvement. For the others, it is basically stable. For the regression, we have seen that although GPT-4o Mini is better for human eval in terms of logic, we have seen regression by 12% for Big Code Bench, which is huge. This is maybe explained by the fact that Big Code Bench is more diverse, so we cannot really rely on Human Eval Plus. Then the other regression, we've seen a slight 2% regression for syntax error, and the huge regression, the more prevalent regression was for missing declaration and import. It's up to 50% with Big Code Bench. This may indicate that given the diversity of the tasks in Big Code Bench, we have many libraries that at LLMs are not able to import them all properly. And for improvement, we've seen improvement by 65% in terms of time, but not that improvement for Big Code Bench. This could easily be explained by the fact that Human Eval Plus is basically programming as tasks, so we can see more the impact of optimization. For the second scenario, we have the GPT-4o vs GPT-4o Mini. We have improvement in terms of logical correctness, improvement in terms of the missing declaration and import, but the impact of having a smaller and more cost-effective is clearly in time regression. So GPT-4o Mini generates codes that are less efficient in terms of time. Overall, we did not see impacts on memory improvement or regression, and the other aspects are overall stable. So this is it, our evaluation. Now for the conclusion of our talk today, we started by proposing a taxonomy of inefficiencies in LLM-generated code. Then we proposed ReCatcher, our framework for LLM regression testing for code generation. ReCatcher takes as input two LLMs and generates a comprehensive report across many dimensions of code quality. And ReCatcher, the goal of it is to assist LLM practitioners and researchers during model migration, and they make their choice themselves. As a result, we tested the regression between GPT 3.5 and GPT 4.0. Between 4.0 and 3.5, we have seen like huge regression in terms of missing important declaration. GPT 4.0 mini showed regression in terms of performance relative to GPT 4.0. And finally, correctness, performance, and errors are the most prevalent divergences, while readability and maintainability are more stable. So we suggest to LLM practitioners and researchers to focus more on correctness, performance, and errors while their evaluation. This is the end of my talk for today. Thank you for being here, and I'll be really happy to answer your questions.
Thank you very much, Altaf. Great presentation. A lot of work went into your research, I can tell. Bram, you have your hand up. Please go ahead.
Sure. Yeah. Thanks for the presentation. Great work, and a lot of work went into that. So I got like two questions.
Okay.
So the first thing is basically the taxonomy. So how specific is the taxonomy to LLM generated code as opposed to human written or developed code?
Okay, so the first for your first question about how specific is the taxonomy for LLM generated code. First of all, like LLM generated code share almost the same human written inefficiencies because they are trained on codes written by human. To be more specific to code generation, what we did is that we analyzed 492 of LLM generated code using Code Llama, DeepSeek Coder, and CodeGemma. We focused on only models that are kind of tuned or trained to be for code generation. Then we did open coding, we labeled manually, we constructed the taxonomy, we did like all the process. Then we went for a survey, and the taxonomy was validated with 58 practitioners and researchers, overall highlighting that the results are relevant to their experience, and kind of mentioned that is overall a complete taxonomy of these inefficiencies, with a bit differences according to percentages of frequency, since they are using like more private model GPT-4o and Copilot. However, we focused on open source, but the categories are the same.
Okay, so all that is true, but if you look at the specific element, your taxonomy, there's nothing LLM specific in there. I mean, the percentage are specific to like a specific model.
Yes.
But if you would look at human written code, you would probably get the same.
Yes.
Thing. So yeah.
Yeah, like LLMs are trained on human written code, so they will reflect also the same inefficiency.
Yeah, so it would be interesting to check actually compared to humans percentages for these categories actually. Yeah, that's
yeah, it's actually a good point.
Cool, right? Okay, thank you.
For your second question,
I'll ask it if there's time left at the end, because some of the people with questions.
Okay, I'll let Rashna go ahead then.
Sure, thank you. Thank you very much, Altaf, for your presentation. I have actually a clarification point. So did you try running tests multiple times to see if there are any variations in the result?
Yes. So for the tests, for the logical correctness, like we are just running unit tests, so like the results are the same if we repeat or not. Also for the static analysis tool, like the results are the same. However, for performance, we repeat the execution of each code 5 times, and then we performed the statistical tests to investigate if we do have divergence between the executions, or it's just like maybe bias, or like just a chance. So we did that, yes. And for the and also we repeated the generation of the code themselves 10 times. So like for example, for the performance, we have 50 repetition. So if we multiply 10 by 5.
Okay, so you tried to run test multiple times, and I am not understanding how did you aggregate it, the results, like, did you take the best of,
The
uh,
results are the average.
okay, okay, average. And just one small question, if I'm allowed to.
No, welcome.
Yeah, sure. So, you mentioned that you validated the inefficiency by 58 practitioners and researchers. I'm curious, what was your approach? I mean, did you send them invite with the different codes generated, or it was a survey, or how it did you conduct it?
Okay, so we did a survey. Basically, what we did is like we mined emails from GitHub of people using LLMs to code generation. Basically, there is some tags that you can use. I can share with you the paper because I know you are working now on a survey. Yeah,
Yeah.
I'll share it with you the paper that have this. So
Okay.
yeah, we have the emails from GitHub, and I think we had like collected maybe if I'm not mistaken, we had a response rate of about 7%,
Mm-hmm.
which is pretty good compared like people
Yeah.
not answering.
Okay, thank you very much.
Thank you.
Thank you, Dashna. Bram, did you have a part B of your
Oh
question?
yes, and even for you, I'll stick with the part B. So
Okay.
so I'm wondering, yeah. So the interesting work. I'm wondering if you're planning to build some kind of leaderboard with your results, or like who would be like your end user for your work?
Okay, so our end user will be people like using LLMs for code generation, or having kind of AI based systems to assist them in code generation. Here in this presentation, I only like showed the results of differences between like GPT family models, but we did also study the impact of fine tuning and merging. So like we did not study like the quantization, but like basically we are saying if I'm putting effort to have a fine-tuned model, uh, will it be better or not? One of the very interesting results that we got is that like we fine-tuned we used for models fine-tuned like using Kotlin benchmark, and we have seen like a huge regression like of 60% in terms of syntax errors, like showing that LLMs are not good when like capturing the information of handling good syntax overall many programming languages. uh, like our end user will be like either evaluating your model adoption techniques across many dimensions, and also like for practitioners to make informed decision if they want to migrate from, I don't know, like from GPT-4 Turbo to the O1 version that's like so much expensive.
Cool, thanks.
Okay. If there are no further questions for Altaf, I'd like to thank her very much for a great presentation. Thank you, Altaf.
Thank you for attending my talk and supporting me. Bye.
Thank you.
And good luck, Musfiqur.
And
Thank
we'll
you.
proceed with Nushi next. Nushi, please go ahead.
Sure. All right. Is everyone able to see my screen? Okay.
Yes, but please make it a slideshow view.
Yes.
Thank you.
All right. Good morning, everyone. My name is Musfiqur Rahman. I'm a PhD student at DAS Lab at Concordia University under the supervision of Dr. Imad Shihab. And this morning, I'm going to present our recent paper on the impact of environment configurations on the stability of AI-enabled systems. But before getting into our paper, I want to show a few memes. Well, we software engineers have seen these memes a lot, right? It works on my machine. There are so many different variations of this meme. Now, the question is, why does this meme exist? Well, we know that this has happened. It has been happening for a very long time that something, a system works on one environment configuration, but does not work on another environment configuration. Now, there can be various different reasons behind that. One of them probably is that environment configurations are not the same. Maybe we have similar environment in development testing, but production is completely different. In the development, we have Linux and Python 3.6, whereas on production, we have Windows and Python 3.8. And this is especially true with open source softwares because the users have the ability to actually install something from the source code, right, on their personal machine. Now, well, this is a known fact. Then why is it interesting now? Well, things become more complex when a system has AI component. In a system that has AI component associated with it, integrated with it, even if you make sure that a system builds and run on different configuration settings, there still can be other challenges. So let's take a look at an example here. So let's say there is a face recognition system, which on the development environment, it builds and run on Linux and gives you an F1 score of 0.9, 90%. But when it's on the production environment, which runs on Windows, it still builds and runs, but the F1 score drops from 90% to 86%. Now, this is also a known issue. This has been reported in existing literature. So the question we have to ask ourselves is that, well, even though the system builds and runs on different configurations, why do we see this sort of unexpected behavioral difference? And this unexpected behavioral difference is what we call instability of an AI-enabled system in our research. So the interesting questions to ask is, how does change in operating system affect the system's behavior? What other environment factors besides the operating system can cause this thing? And this is the motivation behind our study here. So we know that AI-enabled systems can be affected by operational environments. As I mentioned, there have been a few reports of that in the literature. And when we run the same AI-enabled system in different configurations, we can see this sort of unexpected behavioral differences or instability. So develop and from before, we know that it is not guaranteed that always the development environment and the deployment environment are going to be similar, right? It's very much possible the development and deployment environment can be different. And this is the reason why being able to quantify and understand the extent of instability an AI-enabled system will show across different environments is crucial. So to understand the issue of instability across different environments, we study 30 open source AI-enabled projects. All of them are primarily written in Python. We run them on Travis CI with different configuration settings, and I'm going to talk more about the configuration settings in the upcoming slides. So at first, we built those 30 projects in Travis CI. Using their existing travis.yml file. So those who have used Travis CI, we know that there is a configuration file associated with Travis to build and run something on Travis CI. So we keep the existing Travis CI file without making any change to that, and just try to build these 30 projects on Travis CI. Because there are projects, we found some projects which have the travis.yml file, but it still does not run on Travis CI. The first step was to get these 30 projects run on Travis CI. Once we were able to do that, then the next step number 2 was to edit the travis.yml file so that we can include all the configuration settings that we want to study. And finally, once that's done, in step number 3, we compared the performance of models across different configuration settings to analyze the instability. And in order to do that, we perform 2 statistical tests, Mann-Whitney U-test and Phillips delta. In the arbitrary example, although I just showed that, well, the model's performance in F1 can vary, model performance is not the only metric that we considered in this study. We also considered processing time and expense, because given the fact that an AI-enabled system will have machine learning models, and machine learning models will have to be retrained in a given interval, understanding how long it takes and how much money is associated with that is also interesting, to know. The environment variables that we studied in this research was for operating systems. We studied Linux, Mac, and Windows. Within Linux, we also looked at 3 different distributions: Genial, Bionic, and Focal. We studied 3 Python versions: 3.6, 3.7, and 3.8, and 2 CPU architectures: AMD64 and ARM64. Now, before moving into our research questions, I want to show you an example of the travis.yaml file and how we configure the Travis file to run different configuration settings. So on the right side on my screen, you can see an example Travis YAML file. In this file, you can actually define multiple jobs, and each job can have its own configuration, environment configuration. For example, I have 2 jobs here. The first one is using a virtual environment where the Python is 3.6, the operating system is Linux Genial, and our CPU architecture is ARM64. So that's for our job number 1. Then I have another job defined, job number 2. This uses Python 3.7, operating system Linux with distribution Bionic, and CPU architecture is AMD64. So in the Travis CI file, I'm just showing, in this particular case, showing 2 examples, but we defined all of the configuration variables that we wanted to study. Now, before like as I mentioned, I'm going to talk more about the configuration variables that we studied. We defined one baseline configuration which had Linux Genial, Python 3.7, and AMD CPU architecture. And every time we wanted to study the effect of one specific environment variable, we only changed that variable from the baseline configuration. For example, if I wanted to study the effect of CPU architecture, I will change only AMD64 to ARM64 from the baseline configuration. The reason behind that, if I see instability between the baseline configuration and the other configuration, I know that it is happening just because of that one particular variable that we changed, nothing else. So again, every time we run an experiment, there is always one environment variable that is different from the baseline configuration. We run each project 50 times in each environment configuration so that we can mitigate any randomness or any sort of unaccounted for variations. All right, now let's move on to our research question. Our Q1, we wanted to understand how much instability is introduced by changing the operating system. And this is the big table with a lot of numbers. Don't worry, I'm going to walk you through all the numbers in here. So here we see that in the row in model performance row under Linux versus Mac, 7 or 23.33% of the studied project. 7 out of the 30 projects showed instability when they were run on Mac versus Linux. Out of the 7, it doesn't necessarily have to be the case that we see instability and it's always big. So it could be like we break down the instability into 3 effect sizes: small, medium, and large. So out of the 7 projects that does show instability on Mac OS, 6 of them actually show large effect size, while 1 of them show as small effect size. Similar to this between Linux and Linux and Windows, 6 out of 30 projects, 13.33%, show some sort of instability when run on Windows, and all 6 of them show large effect size. In processing time between Linux and Mac, 29 out of 30 projects show instability, and 29, all of them actually show large instability. Between Linux and Windows, 30 out of 30 projects show similar sort of instability, 29 of them show large. And for expense, all projects, whether they run on Mac or they run on Windows, they show instability with large effect size compared to Linux. Now that's about the operating system. What about the distribution, different distribution of the same OS? Well, let's get Genial versus Bionic out of the way, because as you can see, it's all zeros. Genial and Bionic produce identical results across all primitives. But when we look at Genial versus Focal, 3 out of 30 projects actually show instability in model performance. 2 of them are large. And 23 out of 30 projects show instability in processing time and expense. And I want you guys to pay attention to this particular column in here. By now, you probably already understood that not all projects will show instability, but when a project does show instability, it's more likely to be large effect size. So, well, these are just numbers. Which OS or which distribution shall we use? So we dig deeper into and compare the different operating system and distributions, and we find that on Mac OS compared to Linux, performance increase can be achieved, which is on average 1.44%. That's a good thing. The performance of a model increases when you run it on Mac. However, that comes with an additional increase in processing time of 137%, and expense increases by 85.47% on average. So probably it's not worth it to gain 1.44% performance and then spend like this much amount of additional money by running something on Mac. Compared to Linux and on Windows, performance actually drops. And on average, 4.21% performance drop was observed. Processing time and expense both go up at a rate which is similar to macOS. Comparing between Genial and Focal, you can achieve 2% performance increase on Focal. However, that will also come with 7% increase in processing time and expense. So the key takeaway from our research question 1 is Linux is faster and more cost effective than Mac or Windows, and the newer versions of Linux tend to increase processing time and cost slightly compared to the older version. All right, now let's move on to our Q2. How much does changing the Python version introduce instability? Well, between Python 3.6 and 3.7, the performance processing time, expense, everything was identical. We did not find any instability at all. However, between Python 3.7 and Python 3.8, 5 out of 30 projects show instability. 4 of those were large effect size. In terms of processing time and expense, 24 out of the 30 projects actually showed instability when they are run on 3.8. Once again, similar pattern. When instability exists, it's more likely to be large. So which version of Python to use? Well, the 3.8 over, if you choose 3.8 over Python 3.7, there is a chance of on average maybe 0.73% performance drop will occur. Again, it's not a huge, it's not a big number, 0.73% performance drop. However, you're running something on Python 3.8 will require you to spend 5.3% more time and money. So compared to Python 3.7, Python 3.8 is less efficient in all 3 metrics that we studied. Finally, in RQ3, we move on to hardware configuration, and we ask the question, how much does changing CPU architecture introduce instability? Again, we see a similar pattern. In model performance, only 6 out of 30 projects show instability. However, for processing time and expense, 28 out of the 30 projects show instability. And again, majority of the projects that do show instability show a large effect size. So comparing ARM64 with AMD64, if you run your system on ARM64 CPU, then there is a chance of, on average, maybe 0.62% performance drop will happen. But at the same time, it will also come with 25% increase in processing time and expense. So for RQ3, the takeaway is, very few projects show instability in model performance. However, if you run something on ARM64 CPU, it is going to incur higher processing time and cost than AMD64. So the key insights and implications. We found that instability is more common in processing time and expense than the model performance. However, to the best of our knowledge, at this point in time, there is no automated way of determining whether a system will show this sort of instability or not without running them on different configuration settings. So our suggestion is that developers actually should run their build and run their systems across multiple configuration settings before deployment. And also, in order to reduce the risk of instability, developers should adhere to dev prod parity, which states that we should keep our development environment and production environment as similar as possible. And finally, again, by running a system on multiple environment configurations before deployment, the developer will be able to find the most optimal configuration setting that gives the best performing AI-enabled systems. All right, so to summarize, again, we wanted to study the effect of environment configurations on the AI-enabled systems because we cannot guarantee that the development environment and the production environment will always be the same. And our findings reflect that Linux is faster and more cost efficient than Mac, and newer versions of Linux tend to be more expensive and take longer to process. Also, Python 3.8 is less efficient in compared to Python 3.7 across all three metrics that we studied. And ARM64 again incurs higher processing time and cost than AMD64. So you can find our paper on this link, a more detailed version of what I've just presented. And yeah, that's all from my side. Any questions?
Thank you very much, Mushi. Maybe if you leave up the QR code, yeah,
sure.
We'll give people a chance to scan it if they'd like to read the paper. Thank you very much. Okay, lots of hands raised. Maybe we'll start with Jasmine. And yeah, go ahead, Jasmine.
Thank you. Thank you, Mushi, for your talk. Very interesting. So this was more about AI systems and stuff like that, but how much of that do you think applies to software dependencies, right? This is like a really, really big issue, especially now that the hardware is changing so much, right? When the M chip came out, nothing was compatible with it, basically. So how much do you think of what you talked today applies to dependencies?
Well,
and how do dependencies constrain AI development related to that also?
I mean, when I was, so the three Python versions that we used when I was in our study was Python 3.6, 7, and 8. And I already found that the moment your version of Python changes from 3.7 to 3.8, things starts breaking just because the version of, let's say, Pandas is not compatible with Python 3.8, which is compatible with 3.7. So to go back to your question, how much does it affect the dependency? I mean, it does affect dependency a lot. Like I personally looked at only the programming language, but if you go deep within the programming language, I'm sure versions of dependency of different libraries are going to give you similar type of result. In this particular study, we had to we were able to study these 30 projects because they ran in all Python 3.6, 3.7, and 3.8. But there are more projects that we started with which did not really run because of this issue that they were built for Python 3.6 and 7. The moment we wanted to build it on Python 3.8, because of library versions, they just did not run. So I'm sure like there is a dedicated research on this instability type because of the libraries issue and dependency issues out there.
Thank you.
Adekunle, you have a question?
Yeah, actually, he already answered my question because I wanted to ask about the versioning of the of this Python. Maybe I was thinking maybe the higher the version of the Python, the lower the performance of the performance here. But based on what he already said, he explained towards that direction that maybe it's because of the dependency of a thing that maybe the programs were developed for some versions and definitely they will not be able to excuse me, perform in any other version. So he already answered the question. Thank you.
Okay, great. That was easy. So I'll let Diego go ahead with the next question.
Right, Mushi, thanks for the great talk and very interesting project. I think we've talked about this before. So I wanted to clarify one thing. So what you're measuring here is the CI build and test, right? Rather than the
so what we're measuring here, well, in terms of performance, it's like there is a specific task. For example, it's a classification task, and we are performing how accurate what is the accuracy of the classification task on different environment configurations. In terms of processing time and expense, yes, this is based on CI build. Like we started calculating processing time from the moment when the virtual environment started to run all the way up to the final task that we have assigned defined in the configuration variable. Yes.
Right, and okay, that I think that makes sense to me. And did you look into, maybe there are tests that are specific for different platforms? So some projects have platform-dependent tests, right? Which could explain Why maybe in Mac it takes longer or takes less time because you're
Yeah.
testing less instead of
Yes.
possible.
Yeah. I mean, this can be another. The thing is that the project that we studied, we manually went through these projects, and some of them are very domain specific, and we did not have the enough knowledge to understand exactly what
Right.
tasks were. Like, for example, there was several projects that were from the domain of astrophysics. I had no idea about like exactly what those tasks are, other than just running example models that they made select some sort of prediction. So yeah, there could be tasks that are system specific, but the 30 projects that we studied and I manually observed, there was no specific, kind of statement that showed that, well, these projects are built for a specific platform.
Yeah. Okay, maybe a very quick follow-up. Sorry, Bram. I guess like if you run the same models twice, like without any change, you expect some changes, right? There's no determinism.
Each module was actually run 50 times. So we
Yeah,
ran
that was my question. So you run like 50 times, you said, and then
50
you
times. That's
compare
right.
the distribution, right?
That's right. We compared the distributions. Yes, that's right.
Yeah, pretty cool. Thank you.
Okay, great. Thank you, Diego. And Bram?
Yeah, so yeah, interesting work. So, with a similar question as for the previous talk. So, how specific are your findings to AI projects? Like, if you would do the same experiment, but actually with non-AI projects, in terms of stability of the Python version and so on, like, how different would the
Yes.
findings be?
It does not necessarily have to be very specific to AI project. We studied the AI-enabled systems, but it is very likely that the same sort of findings can be observed even if we run the same experiment for projects that does not have any AI version. The thing is, AI-enabled systems have some machine learning component, and those machine learning components are not deterministic, right? So there is uncertainty associated with ML models themselves. So what we're trying to say is that, well, we have this, something runs on one machine but does not run on another machine. That challenge is there, but now with AI-enabled system, we have one additional challenge that the models themselves are also not deterministic, and there is a lot of uncertainty associated with that. But again, but going back to your question, the same findings probably can be observed in projects that does not have any AI component either.
Yeah, so I think it will be important to have a kind of baseline of some non-AI project, because what you're saying is that there's the component of instability brought by all these different factors, but then there's also the component of model, which has also non-determinism. And I think what you're saying is that you actually want to figure out if you add on top the model's instability, does that kind of like completely blow up the situation, or is it just negligible compared to just without?
That's right.
So you probably need some kind of baseline to really figure out how different are the findings compared to non-AI.
Yeah, I think that's a good idea to have the baseline without the AI components as well.
And the other point is, so if you could you go back to your slide 12?
Wow.
Because I got a similar comment actually for the other RQs as well, but no, actually, I'm sorry, the next slide, the one with the takeaways. Yeah, so Linux faster, more cost effective, and then you say you should use Linux. So it's causation versus correlation. So I have to
that's
be
right.
careful.
Like, we cannot say that. Like, we're just reporting our findings in here. The difference between focal and Strenial is not that huge. So I don't want to say that just because of this finding from this 30 project, someone just should keep using Linux and not Mac or Windows. But it's basically from all the projects that we studied, Linux tend to be faster. And again, the processing time and expense are also correlated with each other, right? So when something takes longer, it will, you'll have to spend more money on that. So Linux, basically specifically for Travis CI platform, Linux are much faster compared to Mac and Windows. So I probably will say, like, if you're using Travis CI, go with Linux, but like it cannot be generalized for other CI platforms, probably.
Yeah, but again, you're kind of making kind of really strong conclusions there. So maybe you just need to rephrase a bit, like the applications. Good. I mean, yeah. So I mean, the findings there, just like the way you sell it, I think just needs a bit of some rephrasing, I would say. Yeah.
Yeah. Thank you.
Yeah, maybe I can jump in because I don't see any other hands raised, and I think it would be nice to like follow up with this. Like we trying to have a more deeper investigation as to the reasons as to the performance changes, right? So,
Yeah,
I mean, there is kind of a gut feeling I have that like the CI pipeline itself is more likely to explain the differences than the AI component, right?
okay.
Which then then implies, yeah, like there are differences between execution profile of different platforms or for Travis CI, but which we kind of know as you kind of motivated the project based on this, right? So traditional
Yeah.
software doesn't work on all platforms as intended. So it'd be very nice to see, for instance, if you change like the version of the library that works with ML, like the version of the PyTorch, right?
Mhm.
Does that make a huge difference? Because now you're only changing the AI component part, and
That's right.
you
Right.
might be able to sort of narrow down your scope, or
Yeah.
or even have like some well-known tasks or benchmarks running on different platforms, and you will see that they're probably going to find differences there as well. So you kind of
Yeah.
isolate the AI component a bit more, right? Yeah, cool.
Absolutely. That's a really good idea. Again, in our study, we were not able to pinpoint exact reasons behind, as
Yeah.
Dr. Bram also mentioned, like it's causation versus kind of correlation. We were not able to say why this is happening, that what's the cause behind that. But yeah, as you mentioned, like pinpointing exact things will help us to make a causal relationship between like the results that we're seeing. For sure, this can be a very good future research.
Perfect. Thank you.
Okay, we actually have one more question from Tina Yang from the audience. She wasn't able to raise her hand, but Tina, please go ahead.
Sure, thank you. Yeah, I think it's very interesting to see how the model behave differently on the different hardwares and different configuration. But coming down to isolating the environment, I was just wondering, have you thought about using Dockers and making sure the infrastructures, the version of the Python that you're testing are consistent, right? So yeah, go ahead, sorry.
Yeah, I mean, like the reason behind why we suggest to, to adhere to the dev prod parity or use things like Docker is so that this sort of instability does not happen, right? So no, in our study, we did not use Docker because our focus was to kind of find whether instability exists or not, and to some extent. But if you use Docker, again, the purpose was just the opposite of why Docker is used, right? But again, going back to your question, using Docker and the dev prod parity principle will help reduce the risk of instability.
Right, exactly. So then we're on the same page. I guess because when you open up your presentation, you pose as a question of how to isolate the different configuration instead of truly understand if it happens in those configuration, what works better and what not, right? So I guess that was a slight misunderstanding for me to understand your opening reasoning for the research. So yeah, okay, thank you.
Thanks.
Okay, thank you, Tina. Are there any more questions from any of the participants for either speaker, Mushi or Altaf? No? Okay. Well, I think that was an excellent training talks today. I'd like to thank both of our speakers again for their presentations and for sharing their research. And thank you for such a great turnout during this Reading Week edition of our training talks. And I look forward to seeing. Oh, Rashna, you had your hand raised still. Did you want to jump in with another question?
No, Lori, I was clapping.
Oh, you're clapping.
Yeah.
Oh, thanks for clapping. Yes, and Hassan is clapping. Everyone's clapping. A big round of applause to our speakers again. All right. Thank you very much, everybody. Have a nice day.
Thank you.
Thank you, everyone.
Thank you. Great talks.
Thank you.
Thank you.